Right, so the last technical talk before our sponsorship talk is about introducing effect handlers into WebAssembly.
Okay, great. My name is Luna Phipps-Costin. This is Continuing WebAssembly with Effect Handlers, and this is joint work with the people whose names are on this slide. So I'll introduce WebAssembly. It's a programming language intended to express programs in a number of different languages, and it is designed to be executed quickly in a portable sandbox with predictable performance. So I'll give a quick overview of what it actually looks like. It has flat stack-based instructions, and it has structured control flow. It has a type system that can enforce the stack shape and the type of operators. And we have function pointers, but functions don't capture their environment, so we don't have closures. And it's designed to not require garbage collection at all. So here's an example of what WebAssembly looks like. Each of these, this is just a sequence of 3 instructions. The first 2 push to the data stack, and then this add instruction pops values off the data stack, adds, and pushes a result. So these reduce to the expression on the right. And we can type these instructions, capturing the intuition that the constant pushes an integer on the stack, and the add expects to on the stack pops them and pushes a 3rd integer. The structure control flow can be a little bit confusing, but it's going to be relevant, so let me introduce it. This loop instruction is not a loop. Both the block and the loop are semantically equivalent to their contents, which is a sequence of instructions, with the exception that they each introduce a label. When we use the BR instruction targeting a label, control moves to a location depending on the nature of that label. In the case of a block, control moves to the end of the block, this right pink parenthesis. In the case of a loop, control moves to the beginning of the loop, so the left parenthesis. So now that we know what WebAssembly is like, sort of, let me talk about an issue for WebAssembly, which is that a number of programming languages that are popular and that care about WebAssembly have some sort of non-local control flow that's central to their identity. Things like lightweight threads, like iterators, like async and await. And by the nature of these control flow features, they're not trivially expressible using WebAssembly's call and local control. So the current popular solution is to do some kind of transformation on programs to resemble continuation passing style. And to reduce engineering burden, we can do this at the WebAssembly level, so we can share a single tool called Asyncify from Alan Zakai and the Emscripten team. Because of the constraints of WebAssembly, this requires doing things like splitting locals to memory and branching on calls. And so there's some cost to this, both in time and program size, and also just kind of the engineering burden of using this large tool. So we look to Plotkin and Pretnar's effect handlers for inspiration for a different solution. And it turns out that effect handlers fit extremely well for this use case. So, we know they're very well researched. We just heard a bunch of talks about them. They're expressive enough to express all of the control that we've just talked about. All of the operations of effect handlers can be effectively typed in the WebAssembly stack-based type system. And recent work has shown that it can admit performant implementations, and we also just saw more of that. I want to briefly point out run and def control because our effect handlers are very similar. We have typed control tags and thus effect forwarding. That's the main difference. And also that despite all the discussion of type and effect systems so far, we don't extend the WebAssembly type system. We don't want to extend it, so we have no effect system. So let me capture the intuition of what it's like to implement non-local control. So imagine that we want to implement, for example, lightweight threads in some interpreter. Well, to do so, the obvious thing to do would be to modify the interpreter to capture any information relevant to a given lightweight thread. This would be the current control, maybe any thread local state that's necessary, and reify this into some object. Maybe we'll call it a context, and maintain a queue of these contexts. And then we can do simple round-robin scheduling, dequeuing contexts, passing control to that context, and then in some way pulling out and continuing to schedule. And what's captured in that explanation is that what we're doing is reasoning with, capturing, and resuming suspended computations. And these are continuations. So what we want to do is provide faculty so that we can implement this control flow as a library. So, implementers of non-local control for a language that targets WebAssembly can implement this control flow in the runtime of their language, which is compiled to or written in WebAssembly. And so okay, if we want to do that, provide system stacks, right? And we can access the stack pointer maybe, or set jump and long jump. But WebAssembly isn't intended to be portable. This is not portable, and it's gratuitously unsafe. So we want to provide some alternative to these low-level primitives. And so effect handlers are what we do. And I will bring up two kind of ways of understanding this, because I haven't actually been kind of explained semantically yet today. So one is that handlers can allow us to dynamically assign a semantics to operations. Like we might have an operation to yield a value for a generator, or an operation to defer to the scheduler for lightweight threads. And so we can dynamically assign a semantics to those as a library. And then the other one that tends to help is people are familiar with exceptions. We're familiar with having a handler for some particular class of exception that's somewhere in our dynamic extent, and when we throw control passes to the handler. But of course, the main difference is that we can then resume one of these exceptions, and we can even store away that resumption for later. So we extend WebAssembly, and we call this WasmFX. And the extension is fairly minimal. The things I'll point out is that we can declare control tags, which represent an operation. And we have 3 core instructions that allow us to work with that. Cont new accepts a function pointer and allocates a continuation. Resume accepts a continuation, installs a handler, and passes control to the continuation. Suspend suspends to a given operation, the nearest handler for said operation, and also passes the current continuation. And even though the syntax is a little bit weird, it's also a little bit different because we can't rely on garbage collection and closures from what we might be used to. So I think the best way to get into this is actually an example. On the left, we define a reschedule operation. And this is just a name that I've chosen. There's no reschedule syntax in WasmFX. But then we can use that in a process. So I've written this function that prints 1, and then performs the reschedule operation, and then prints 2. And that's all I've written. So we need to actually assign a semantics to reschedule in order to run this function. And we can do that in our scheduler. So on the right, we have a scheduler. And please bear with the WebAssembly syntax for a minute. This actually is fairly simple and resembles just a simple round-robin scheduler. So the highlighted part is just entering a loop and dequeuing a continuation representing a thread off of the queue. And then we can resume that continuation, passing control to that continuation. And so if we imagine that that continuation is representing our process, control passes to that process and now prints 1. And when we perform the reschedule operation, control will pass to a handler that we installed. And actually, when we resumed, we associated the reschedule operation with these 4 lines that I've highlighted. So now control passes to our handler for reschedule, and it also passes the current continuation. So our semantics that we're going to assign to reschedule is that we're simply going to enqueue the remaining continuation of that thread back to our round-robin queue, and then loop to continue another thread. And so after we've run some more threads, we might come to this process thread again in our queue. And when we resume, because we enqueued the remaining continuation, control is going to pass to the printing of 2. And when this function returns, we can execute our return handler, which simply continues with the next thread. And so spawning this process is as simple as allocating a continuation representing it, and then enqueuing it. So I'll go into the 2 most interesting instructions in a little bit more detail. So this resume instruction is syntactically a little bit weird. In a bytecode, we prefer non-nesting instructions for a number of reasons. And so rather than include blocks within resume, we associate tags or operations with labels. and those labels represent our handlers. And because of how blocks and branching work in WebAssembly, what I've written here actually associates the final line as the handler for the T operation, because it's the end of the handler block. And when we return, control passes directly after the resume instruction. So we can think of our return handler as simply following the resume instruction. That's highlighted as well. We also have this continue instruction. And people who are familiar with the traditional treatment might also wonder, why don't we allocate a continuation when we, for example, install a handler? Well, we want predictable performance characteristics. So with this treatment, we know that any use of continue allocates a continuation and nowhere else does. And it also makes sense ergonomically because we can't use a block or a closure because we can't allocate closures in WebAssembly. And we also want to be able to install handlers on existing continuations. So resume accepts a continuation as an argument. And the other thing that I want to point out is that we do have one-shot continuations. This is, again, because we don't want to be able to create cycles. We don't want to require a garbage collector. And the good thing is that we can express all of the non-local control that we are concerned with one-shot continuations. And this is enforced dynamically. I'll talk briefly about our prototype implementation and preliminary results. So we do have an implementation in a production WebAssembly implementation, and we do use real system stacks to represent the continuations. So we have a complete implementation, but it is experimental and unoptimized. For example, we take on the cost of using existing library functions to perform non-local control. We have two benchmarks. One is a benchmark measuring raw task switching throughput. It's written in C. And this is a particularly hard benchmark against asyncify because while we're measuring switching between stacks, asyncify is simply representing this with branches and calls. And we also have a code size benchmark, which compiles Go programs, both using asyncify and using WasmFX. So here are our preliminary results. WasmFX performs within an order of magnitude of asyncify on raw task switching throughput. And these are initial numbers. We hope to do more optimization and see that be caught up on. We also see in code size that WasmFX consistently outperforms asyncify. And this best case example is a handwritten version of the control flow. So I've talked about what WebAssembly is, why it needs non-local control flow. I've talked about how effect handlers fits in this need and how we adapt effect handlers to WebAssembly. I've shown that it can express the needed control flow constructs, and most of the other control flow you might need is in the paper. And I've shown that we can implement it effectively. So thanks for coming to and listening to the talk, and I would be happy to answer any questions if you have any.
Thank you. Thanks for the nice talk. Are these, I think I know the answer, but I just want to be sure. Are these shallow or deep handlers?
They're actually sheep handlers.
I was afraid. Yeah, okay.
They're shallow in the sense that the handler is not automatically reinstalled. However, we only install handlers when we use the resume instruction. The resume instruction installs handlers and passes control. So this has performance benefits.
Okay, thank you.
I'm wondering, what is the path to standardization or adoption for this feature? Are you getting any pushback either on the feature as a whole or for alternative implementations of, alternative representations of this to implement the same kinds of high-level language features? What does that look like?
There's lots of appetite.
Fantastic.
I have maybe a naive implementation question, but so you say one-shot continuations, but in most of these effect handler languages, they have that you can use the continuation many times and implement these weird control flow and coin flips where you evaluate it multiple times, right? So can I actually use this to implement those kind of effect handlers efficiently, or do I still need to do the same kind of stuff that Asyncify does?
So you're not going to be able to do probabilistic programming, but all of the control flow that like languages care about that we have in our paper can be done with one shot.
Okay.
Go ahead.
No, you go ahead.
So maybe just a follow-up to Will's question, but there is a standardization process, right? Is this in the standardization process, or is like interest in maybe creating the standardization process in the future?
Sorry, I should have been more explicit, but I don't want to bore you all. There's appetite as standardization is in progress, but there is politics and controversy.
Yeah, okay. Is it at a particular stage?
Stage one.
Okay, good. Awesome.
More than 0. Stage 4.
A quick question, technical. Can continuations close over things?
Yes, so because they're one shot, it's actually really easy to provide a value to them. So we have a cont.bind instruction.
Oh, that's cool. So WebAssembly doesn't have closures, right?
That's right.
Can I encode one-shot closures by misusing continuations as well?
Absolutely.
Beautiful. Thank you.
That's really interesting. Okay, so this is maybe a more speculative question, which is why I left it till last. But do you have a sense for how much performance is left? Right? Is the technique you're using fundamentally more difficult for this benchmark than the one you compared to, or do you expect you'll be able to get close to the continuation passing style version?
This may be like my personal opinion. Beyond like really the like very cool tricks that we just heard about, I think there's still going to be a gap with Asyncify on raw task switching, because Asyncify is essentially like cheating on that benchmark by just like being able to switch its own internal state and boom, you've switched task. But I think for like actual benchmarks, there's a lot of performance to be had and to be gained.
Fair enough, thank you.
Without support for garbage collection, is there a way for a continuation that you are not invoking to clean up any resources it might have allocated?
Yes, so we have an instruction for that. It's called resume throw, and it just resumes and immediately throws an exception.
Thanks.
All right, let's thank the speaker.